Hi, I'm Prasoon Goyal, and this is joint work with Scott Niekum and Ray Mooney at UT Austin. Let's say we want to use reinforcement learning to train a policy for the task shown in this video. For this, a reward function is often hand designed. As the number of tasks grow, we'll need to design a reward function for each new task, which is a very cumbersome process. In this work, our goal is to use natural language descriptions such as rotate the red handle down to make the reward design process easier. The diagram here shows our overall framework. The setting consists of the standard MDP formalism with the agent environment loop plus a natural language description of the task. We augment the MDP loop with the PixL2R module, which stands for pixels and language to reward. It computes a relatedness score between the current trajectory and the given natural language description, which can be used as an additional rewards on top of the extrinsic rewards from the environment. The module is trained using supervised learning with language data collected using Amazon Mechanical Turk. Next, I'll talk about some of the details of the PixL2R module. It is a neural network wherein a CNN is used to encode the images and an RNN is used to encode the language. The two encoded inputs are then concatenated and passed through a sequence of fully connected layers to predict the relatedness score between the two. We use two types of data augmentations. First, each frame in the input trajectory is dropped independently with a fixed probability. This reduces the size of the input and also makes the neural network robust to minor variations in the trajectory. Secondly, we use partial trajectories in addition to full trajectories. So if the input trajectory contains 10 frames, we only use the first k frames as the input to the neural network, where k is varied from 1 through 10. Training with partial trajectories is important because the module needs to make predictions on incomplete trajectories during policy training. We model the training as a regression problem where complete trajectories have a ground truth score of +1 or -1, depending on whether they are related to the instruction or not, and shorter trajectories have scores closer to 0. More details about the PixL2R module can be found in the paper. Intuitively, here's how we use our trained PixL2R model in our pipeline. Consider these two trajectories. Given the instruction for the task, we can use the trained PixL2R module to infer that the trajectory on the left is unrelated to the language, while the trajectory on the right is somewhat related to the language. These relatedness scores can then be converted to rewards so that the trajectory on the left gets a low reward while the trajectory on the right gets a high reward. Next, I'll give a brief overview of the domain and the dataset we use. We selected 13 tasks from the recently released MetaWorld domain. For each task, we randomly placed the main object and a few distractor objects in the scene to create 100 different scenarios per task. We then use Amazon Mechanical Turk to collect language data for these scenarios. Some sample descriptions are shown in the table here, which gives a sense of the linguistic diversity in the dataset. For example, the words toaster handle and red block refer to the same object. Finally, I'll discuss our main experiments and results. First, we look at the sparse reward setting where the agent gets a reward of 1 for completing the task, while a reward of 0 in all other cases. We compare policy training with extrinsic rewards only and policy training with language-based rewards in addition to the extrinsic rewards, denoted using sparse and sparse plus regression respectively. The metric we use is the number of successful episodes after a fixed number of interactions with the environment. In the plot here, the x-axis shows the number of time steps of interaction with the environment, while the y-axis shows the number of successful episodes. As we can see, using language-based rewards gives a significant improvement over the baseline. The shaded area here shows 95% confidence interval. Next, we run the same experiment with dense rewards that were designed by the developers of MetaWorld. Again, we see that language-based rewards give a statistically significant improvement over hand-designed dense rewards. This is an exciting result as it motivates a new paradigm for reinforcement learning wherein coarse, dense rewards could be designed by hand, and then language-based rewards are used on top of these rewards to get additional boost in policy training efficiency. To summarize, we propose PixL2R, which generates intermediate rewards by comparing the agent's trajectory against a description of the task. Our experiments demonstrate that language-based rewards generated using PixL2R achieve statistically significant improvement in both sparse and dense reward settings. Our code and data can be found at the following link. Please check out our paper and come to our poster for more details about our approach and experiments. Thank you.